Okay, any questions before we continue? Magnetic dipole moment. So what do you find confusing about the magnetic dipole moment?
Direction of 3D objects.
And you?
The distance, how do we measure distance? For example, if a magnetic field is a dipole, at the distance 1, how do we define this?
Okay. Now, what we call the simplest magnetic dipole moment that we can imagine is this one. Just a circular wire carrying a current I. Now, we didn't study what is the magnetic field created by this magnetic dipole moment at an arbitrary point. We don't have the sufficient mathematical tools yet. But we can still calculate the magnetic moment created by this dipole along this line. And this is the line that goes through the center of the dipole, and it is perpendicular to the plane of this dipole. So let's say this is the radius r. We have this ring of radius r, and it carries a current I in this direction. And then what we said was, okay, let's consider a point on this line. And to calculate the total magnetic field at that point, what we need to do is first divide this into very small segments. And calculate the contribution of each one of these very small segments, the contribution to the magnetic moment at that point. So, for example, if you just take this segment at this edge, which is easy to show, and then it is at a distance, let's say L, from the point where I'm calculating the magnetic field, what will be the contribution of the magnetic field? Remember, the magnetic field created by a current carrying wire, we had defined it as the current running through the wire times dl, which is this is a vector which points in the direction of the current, and its length is equal to the length of the very small segment that we are considering, cross r hat, and we also have mu0 over 4 pi r squared. So this is the contribution to the magnetic field of a very small line element. So what will be the direction of the magnetic field created by this line element at this point? Just use the right-hand rule. We have to calculate dl. dl is pointing into the screen. You see, at this point, dl is into the screen. R is this vector over here. So we have this dl vector. This is the r vector. dl cross r, right-hand rule, is a vector in this direction. So the magnetic field created by this very small segment at this side will be in this direction. It is perpendicular to this line. Let's say this is dl1. We are considering this segment. Okay, any questions on how to use the right-hand rule in this case? You can ask me, you can ask your friends.
You said shows the DL and then the R, and then now we do it this way. Could we just use the thumb around the current and this to be direction to be in that way?
Well, you see, okay, this law doesn't exist. So you have this law, the right-hand rule, which basically we will be going to that. We will be showing that the magnetic field created by this field along this line, this current along this line, we can use the right-hand rule that it will be pointing upwards. But first we have to show that. We don't know it yet.
Sure, I didn't mean that. There's just a wire that's coming off, and then we wrap up a hand around the wire to say that the magnetic field by that wire must be around itself.
How do you know? How do you know? This is the law we have. How do you know? We don't yet know that. We will show that. Now, any other questions about, this is the law we have. So if you are making any derivation, eventually you have to base it on this one. And this tells me that I have this wire, just divide it into very small segments. Each segment will contribute to the magnetic field at an arbitrary point, and its contribution will be given by this. For this segment over here, dl is pointing into the screen, r is this vector pointing from my segment to the observation point, and so dl cross r is a vector in this direction. We will discuss it later on. For the time being, for us, it is mu0. Now, of course, we have to sum over all the contributions of all these very small segments. But we can make some simplification in our calculation. We already know that since we are considering a ring, there is a diametrically opposite segment. For each segment you take, there is a diametrically opposite one, which has a dl in the opposite direction. That is, this dl is pointing into the screen, this other one will be pointing towards you. dl is in the opposite direction. So what will be the direction of the magnetic field created by this dl at that point? So this is my dl pointing towards you. And my r vector is this one, r hat vector. So dl cross r is just a vector in this direction. This is dB2. Now the magnitudes of these contributions, let's see, what do they depend on? They depend on the current. Well, both dl1 and dl2, they carry the same current. It depends on the magnitude depends on the distance, r. Well, this distance is, we said it is L. The other distance is also L. Well, they are equal because if you just take, this is my ring. I'm just looking at this point over here. So this point, the distance of this point from this side is the same as its distance from this side, etc. So L is the same. So whoever forgot their yogurt, they can pick it up. So this is also L. So L is the same. Well, if you look at this cross product, the magnitude of the cross product is the product of the magnitudes. Well, r hat has unit magnitude, whatever the direction is. dl, I am taking two segments of equal length. So dl is the same for this segment and also for this segment. And the only thing that might be different is the angle. What is the angle between dl1 and, let's say, this r1? 90 degrees. This is dl, this is r. So this angle is 90 degrees. Similarly for here, dl2 and r2, this is dl2, this is r2, and the angle is still 90 degrees. So the angle is the same. So basically the magnitudes of the contributions to the total magnetic field from this segment and from this segment, they are equal. Now we have these two vectors. Let's see, this is dB2, this is dB1. They have equal magnitudes. Their magnitudes are equal. Now, how do we add them? Well, you just use the parallelogram rule, one thing. This is the sum. Well, how do I know that that is the sum? Well, basically, if you consider this angle, theta, this angle over here is pi over 2 minus theta, and pi over 2 minus theta. They are the same angle. They are of equal length. So if you just sum them up, they're just along this line. This is the sum. So the end of all this discussion tells me that whichever segment I imagine on this ring, there is a diametrically opposite one. And when I'm calculating the total magnetic field, I have to sum over all the contributions. When I sum all the contributions, I will be summing over all these diametrically opposite pairs. And the sum of these diametrically opposite pairs is a vector in the vertically up direction. So this already tells me that it is enough for me to sum the component along this line only. I don't need to worry about the horizontal direction. Now, this was what we had done before and said that, okay, since the total sum will be in the vertically up direction, just keep track of the vertically up components. But let's do the hard way. Let's keep track of everything. So let's see. Now, dB1. Let's say this is the Z component. This is the, let's say, the rho hat direction. That rho hat direction will be constantly changing. Now, what is dB1 in terms of the vector notation? Let's write the magnitudes first. What is the magnitude of dB1? We said that the magnitude of dB1 is equal to the magnitude of the contribution to the total magnetic field from this segment. They are equal, but what is the magnitude? I times dl mu 0 over 4 pi r squared. L squared, right? Because this point is at a distance L. So the vector dB1 what is this vector equal to? You see, what we said was, okay, this is the z-axis, this is the rho hat axis, and this angle over here is theta, because this angle is pi over 2 minus theta. So what is the vector dB1? Cosine theta in the rho hat direction, and sine theta in the z hat direction. So this is dB1. Now the total magnetic field is nothing but the sum of all these dBs. Now let me erase this B1 over here. And which is equal to, well, the magnitude of dB1 is I times dl times cosine theta times mu 0 over 4 pi L squared in the rho hat direction, plus I times, there is the cosine theta, I times L cosine theta over 4 pi L squared sine theta.
So you already have cosine theta inside that.
Where?
Why do we have two cosine theta?
Oh, yeah. So let's see. Okay, you're right. I already have cosine thetas. This is dl this is sine theta well, let's see, mu 0 over 4 pi L squared, mu 0. Okay. Anything else missing? Okay. So let's continue. So the total magnetic field is, well, this sum is over all these small segments making my ring. So let's say B is equal to, I is constant, so independent of which small segment I consider, I is the same, mu 0 is the same. So all those constants, I can just take it out of the summation sign. I mu 0 over 4 pi L is the same for each one of those very small segments. So it is L squared. Cos theta is the same for each one of those segments. Cosine theta and sum over dl rho hat plus sine theta. Well, z hat is the same. Sum over dl. So these are just common factors, common to both of these terms. I took them out. So in this first sum, cosine theta is constant. I take it out. dl remains inside, rho hat remains inside. In the second term, sine theta, I take it out. Z hat is this direction, it's the same. Whether I take this segment over here or that segment over there, that is my z hat. So I can just take it out. I cannot take rho hat out. You see, if I consider this segment over here, this is my rho hat. If I consider this segment over here, this is my rho hat. Rho hat is constantly rotating with the dl, with the small segments I am considering. So that is why I cannot take rho hat out, but I can take z hat out. Now, if you look at this one, the sum over all dl is nothing but the total circumference of my ring. So this is 2 pi times r. Now, let's look at this one. I can just imagine dividing my ring into segments of equal length. So this dl, I can also take it out, in fact. If I take this dl out, what I end up having is I'm just summing over this rho hat. I'm summing this rho hat plus this rho hat plus this rho hat. This rho hat plus this one is 0. This rho hat plus this rho hat gives me 0. So the sum of all these rho hats just gives me 0. So this is 0. And the final result turns out to be I times mu 0 over 4 pi L squared times 2 pi r. Well, let's look at sine theta. This is the angle theta. So sine theta is just r over L in the z hat direction. So that kind of completes my proof. The magnetic field is, well, we can cancel these 2 pi's. It gives me a fact. No, let me just cancel the 2's. I have a 2 over here. This is mu 0 over 2 pi L cubed times I times pi r squared in the z hat direction. And this whole thing is what I call the magnetic dipole moment of this ring. So pi r squared is the area, I is the current, and the direction is also the z hat direction. Now, why the z hat? It's just the right-hand rule. Just turn your finger, curl your fingers around the direction of the current, so the magnetic dipole moment is the direction of your thumb. So the magnetic field created by a dipole along the direction of the dipole itself is just mu 0 over 2 pi L cubed times mu. So what do you mean it doesn't depend on z?
What I mean is it does not directly depend on z. If I want, okay, z equals d distance, how am I supposed to write it in this one?
Now, of course, if you are very far away from the dipole, which is most of the time the case that we are interested in when r is much smaller than z, this we can just approximate as mu 0 over 2 pi z cubed. And in fact, you can just generalize this to the case that mu, the magnetic dipole moment of any charge configuration, is just the sum. If you can divide your system into different currents, the magnetic dipole of the system is just the sum of the magnetic dipoles of each one of those currents. For example, if you have such a system, just two rings side by side, and this is the direction of the current running in this one, this is the direction of the current running in this one, the total magnetic dipole moment of this thing is nothing but mu1 plus mu2, which is I times pi r squared in the z hat direction plus I times pi r squared in the z hat direction. This is the total magnetic dipole moment. And if you want to calculate the magnetic field in the direction of the magnetic, let's say, very, very far away, this magnetic dipole is in fact just a point. And if you want to find the magnetic field along a line that goes through that point and that moves in the direction of the magnetic moment, it is given by this expression. Well, you can consider complicated circuits, not necessarily planar ones. You can imagine this is the, let's say, the x, y, and z direct axis. X, y, and z axis just divided into sum of loops, planar loops just like this one. For each planar loop, you can calculate the magnetic dipole moment and just sum them up. You get the total magnetic dipole moment of the system, just like in the case of the electric dipole. If you remember, we also, when we had a system which is not just plus charge, plus q over here, minus q over there, if we have a more complicated charge distribution, we just write it as the sum of plus and minus charges located at different points, calculate the electric dipole moment of each one, and sum them up. That was the total electric dipole moment. So in this case also, if you have such a configuration, well, you see, this part is in the YZ plane. You can calculate the magnetic dipole moment of that part first, and then consider this other part, which is in the XY plane. Calculate the magnetic dipole moment of that part, then sum them up. Well, of course, there's this region. Let's say the current is running in this direction. Well, there's this region over here where there's not any current running. But that's not a problem, because we are assuming that along this red loop, the current is running in the plus x direction, and along this blue ring, it is running in the minus x direction. The same current is running, so there's no charge flow. Net charge flow through this axis is just 0.
Here the rotating disk, in that case, we divide circles and find each one of the magnetic fields.
Why not? That is one way of proceeding. So the question is this one. If you have a disk that is rotating with an angular velocity omega, and does it have a charge density on it? There's a surface charge density. Then you can just consider that disk, divide it into very small rings, calculate the contribution of each one, and sum them up. This is one way of doing it. And it's correct. I mean, you can come up with many other ways of calculating the same thing. But probably this is the easiest one. Other questions?
Can we imagine a cylinder as in the question that is given in the homework, which has a charge Q? We don't know the density. But can we just quickly show what the magnetic dipole moment is?
Is it a cylinder, an empty one, or a filled one?
A filled one.
Well, that is what we did yesterday, no?
But still, no. My answer was not the same as what we did yesterday, so I'm not sure what I did wrong. So I just want to see.
Okay, just compare your solution with my solution and you will find what's wrong. You see, okay, this is what is the magnetic field created by a magnetic dipole. Now, although in this expression we only considered the simple case of a ring, this expression is, in fact, let's say this expression is valid for any magnetic dipole. If you have a system that has a magnetic dipole, you can consider a magnet, for example. A magnet that, if you know its magnetic dipole moment, then this is the magnetic field created along the axis of the magnetic dipole, direction of the magnetic dipole at a distance z. Of course, assuming you are at a distance very, very far away from your dipole. So if you have such a magnet, a very small one, and if you have somehow determined this magnetic dipole moment to be in this direction, then at this point, which is already very far away from the side, very far away from the position of my dipole, this will be the magnetic dipole moment. Other questions? Yes. True. True. If you have a magnetic dipole here, and you want to find the magnetic field over here, the magnetic field at that point, at this point, this is the vector r, is given more or less like with the same expression, mu0 over 2 pi r cubed. It should be something like, or 4 pi r cubed 3 mu r squared minus mu dot r. That should be the expression. I mean, if you remember, you calculated the electric field at an arbitrary point, created by an electric dipole. It has exactly the same form. Now, how do you derive this? Well, wait 2 more years. I mean, for that, still you need to wait 2 more years. Other questions?
Is it because we don't have sufficient maths?
Because of the maths involved. Okay, let's continue. Now, we will be continuing with induction. We didn't name it yet. Now, but before continuing, let's just relax a bit, lean on your back. Let's try to put what we are trying to do in some perspective. Not just in this course in magnetism, but in general in physics. Now, sometimes, for example, when I'm asking you questions like, which reference frame, you say, well, the reference frame in which Earth is at rest. Think a bit bigger. So we are not trying to understand what's happening in this classroom. We are not even trying to only understand what's happening on Earth. We are trying to understand what is happening in the universe at every place, everywhere. Well, there are a few things that we had already we have tested on Earth. Like we already know that the laws of physics that should be valid in the lab, that you are making some experiments, you are testing some laws, and you are verifying the things that we are discussing in this class, in this classroom. So the laws there, you believe that they are also valid, I don't know, in Germany, in the States, in China. I mean, do you have any doubts that they will be measuring something else? Does any of you have any doubts that it will be different? Yes or no? Okay, no. So the laws that we are trying to study, we have already tested it, that the laws are the same, whether you do it in this department, in the US, in Germany, or in China. So that was easy to test. You just take your setup, go there, go to different places, and repeat the same experiment, and you obtain the same results. Now the problem is, do we know that the laws will be the same in, let's say, in the Andromeda galaxy? Do you have any doubts that it will be the same? You should. That's a good. You should have doubts. How do we know that? Well, we haven't yet gone there. I mean, we haven't even went to the nearest star, which we hope to go by into 20 years. I mean, there have been funding provided to somebody for building small satellites that will be able to go to Alpha Centauri. That's the closest star, and he's being funded by. You have probably read the news, right? There's a Russian guy. He has some funding from the builder of Facebook, and also Stephen Hawking, some billion dollars, and to build some satellites that will be able to go to Alpha Centauri and send back photographs. And hopefully it will be. They're hoping that they will be ready in 20 years. Of course, after 20 years, it will probably take something like 10, 20 years to reach there. And send photographs, it will take like 4 years. So you might be able to see it. You might be able to see just photographs of Alpha Centauri. But even without waiting for it, we are just looking around in the universe. We have been looking at all the stars and all the galaxies. We still can look at their light. There is light coming to us from there. Now, on Earth, we already know how the hydrogen behaves, nitrogen, oxygen. We have all this periodic table. We know their energy levels. We know the types of lights that they can emit. So we can just compare the light we observe from other stars with the lights we have on Earth. And we are also making these comparisons, and up to now, there is no discrepancy. So there is lots of systems in the universe which, in terms of their chemical properties, which determine the light that they emit or they absorb, which have exactly the same chemical property as the hydrogen on Earth. Well, the chemical properties of the hydrogen on Earth are determined by the mechanical laws, by the laws of quantum mechanics, and by electromagnetism. So unless there is a serious conspiracy against us, so all these laws should be valid in all the stars, in all the galaxies. So everything is valid. Now, one problem is this one. So we are looking for laws that should be valid here in our lab, and they should also be valid in the Andromeda galaxy. Of course, until the day that we have some strong evidence that the laws are different. In that case, we will be interested in figuring out what's the cause of that difference. But until that day, at least for the time being, we have all the reason to believe that the laws should be the same. Now, once you go to space, imagine there is no Earth. So there's you, and you look around, and you see me, and I'm just moving. So which one of us is at rest? We don't know. I mean, there's no sense in asking that question. The only thing we can say is that I am moving relative to him and he is moving relative to me. So that is the only thing we can say. So the laws of nature should look the same for both of us. We should be able to find laws that are exactly the same. That is where the problem with this example comes into the game. So we have this region. So there is this region of space, some finite region, which is a uniform magnetic field. And now we put some rod on it. I put some rod on it. We are in empty space. I created this region of uniform magnetic field. How do I create this region of uniform magnetic field? Well, the easiest thing that I can do is I can just take a solenoid over here. This is one of my solenoids. Then I have another one over here. This is another solenoid. Send some current through both of them. So in this region, B is uniform. I can take these solenoids to be huge. So I will have a significant magnetic field in this region. It is almost negligible outside. So I can create such a configuration where only in this region I have some magnetic field, outside almost no magnetic field. I can connect this to a light bulb. And I can just push it with some velocity v. So I'm doing this experiment. We are in empty space. I need some light. It's dark. So what I do is I just create a magnetic field, send my rod, cause my rod to move with some velocity v. And when I do that, we had already seen that, okay, the electrons will be pushed downward. So there will be a current running through my system. Let's call it I. So there will be I. And as the current is running around, the light will just be bright. So now I will have light. This is my reference frame. And I know we had already discussed that the EMF created by this moving rod was just B times L times V. This is the EMF. If the resistance of the light bulb is R, we know that the I is equal to epsilon over R. And furthermore, the power of the light bulb will be equal to I times I squared over R. So there will be some power output of the light. Now let's consider his reference frame. What will he see? Now, I know that I will see this one. The magnetic fields are at rest over there. So what will he see? Well, let's assume that he is moving relative to me with exactly this velocity v. Well, there is nothing that will prevent it. But if he is moving with velocity v in his reference frame, this rod is at rest. Do you agree? So the rod is at rest. So according to all the things that we had discussed until this point, we had discussed electrostatics, we had discussed magnetostatics, we had discussed a bit about the currents in the circuit, which is not really electrostatics, but we applied the principles of electrostatics, and our conclusion was in agreement with our observations up to a certain limit. Now we are kind of trying to do the dynamics. What if things are changing in time? So this is a system that is in my reference frame, this is a system that is changing in time. So as it is moving, there is a velocity v, the position of the rod is changing. So I get my light is just bright. He is looking at the same system. According to him, this rod is at rest. And if he tries to apply the principles of magnetostatics that we had been discussing, there is nothing. There is only magnetic field, but the charges are at rest. If the charges are at rest, then there are no forces pushing them around. If there are no forces pushing them around, then there is no current running through the circuit, so the light bulb shouldn't be bright.
Well, in the reference frame, where we are moving with the rod, the thing is that the magnetic field lines are moving beyond the
True.
So the charges are moving relative to the magnetic field lines, even if we are moving with the rod. Nothing changes.
Exactly. But you see, we have magnetostatics. So now we have electrostatics, we have magnetostatics. So we would like to derive or discover the laws governing electrodynamics and magnetodynamics when electric or magnetic fields are also changing in time. That's what we are trying to do. Well, the first approximation, the first easiest assumption you can make is that assume that the laws of electrostatics and magnetostatics are valid even when we have dynamical cases. But if we have a dynamical case, then we have inconsistencies like this. And we have to somehow solve the inconsistency. And the solution to this inconsistency is what you have just stated. In his reference frame, the rod is not moving, but nevertheless the magnetic fields are moving. So it should be the motion of the magnetic field lines that should be creating this EMF, the EMF of this moving rod. So we should, this expression, we cannot really say that this is a law of nature that is valid in every reference frame, but we can just convert it to an expression which will be valid in every reference frame. Let's say let's call this distance x. And then we said that B times L times V is B times L times dx by dt. Well, for the time being, I'm ignoring signs. I will come back to that sign problem later on. Just ignore the signs. I'm just talking about the magnitudes. V is dx by dt. This is equal to d by dt, B times L times x. L times x is nothing but the area in which the magnetic field is non-zero. So this, we can just call it d phi by dt. And phi b, this is equal to B times A. It's called the magnetic flux. If you remember our discussions of the electric field, we had described the electric flux. We have defined the electric flux as the electric field times the area. This is the magnetic flux. Magnetic field times the area. So this law is now, we can say that epsilon is equal to d phi b by dt is valid both in my reference frame and in his reference frame. Because what's happening is, in my reference frame, the magnetic field lines are constant, but this rod is moving, so that the area in which the area within this loop for which the magnetic field is non-zero is reducing, the area is changing in my reference frame. But in his reference frame, it is the magnetic field lines that are moving. So if you just take this convention, after some time, it will be just two rows of magnetic field lines. After some time, it will be just a single row of magnetic field lines. So this area is changing because of the motion of the magnetic field lines in his reference frame. In both of our reference frames, this will still be satisfied. Yes? It is uniform in a given area. It is zero outside.
If there's a magnetic field outside, we cannot get any EMF.
Well, you cannot create a uniform magnetic field in everywhere in the universe, because the magnetic field lines, they have to close. They have to form closed loops. So somewhere the magnetic field line should be pointing in the opposite direction.
What if we take the rod that is smaller than the magnetic field we create?
In this one? Well, let's see. We can have magnetic field lines over here also. It is smaller. Nothing changes though. So
Nothing changes in that case. What is the difference that we can observe changing?
okay, yeah. So you see, one thing you can observe is, let's say, the magnetic field lines. If you just imagine the magnetic field lines, they are at rest. You're just passing through them. That is something that can be observed. Or you can observe this force. You see, this result we obtain using the concept of the force. So that force you can observe. So even if it is infinitely large, you have a region which has a magnetic, all the universe you somehow manage to fill with a magnetic field uniformly. Still, the force you can observe. And the force will create this EMF. So all these arguments you can still do. Now, of course, there is this problem, though. You're right in one sense. The area, I mean, up to now we have been always talking about the locality in physics. Why did we didn't invent this concept of the field in the first place? So I don't want the electric field over there to influence the electric charge over there to influence this electric charge over here instantly. I define the concept of a field so that the charge over here feels the force due to the field over here. So everything is local. So that's the kind of description we would like to have. A local description, something that depends on the properties right over here only. But then this area, it depends on an area. It's not local. So writing it in this form, okay, it creates this confusion. Here we have a law that's not local. This EMF is created along this line. It's not created at a single point. And this flux is created by all this area, not just a single point. But nevertheless, we will stick with this description until you reach your third year. So most of the things, your questions will be answered in your third year.
I understand the mathematics and how we got to the mathematics, but I still don't understand the physical interpretation of what we just got.
So what we are saying is this one. In one reference frame, I mean, we will be proceeding along this line. What does this mean? So, but what we are trying to do is this one. We have a framework. We have the electricity, we have the magnetism, we have constructed our framework. But in this framework, if we want to make this framework a Lorentz invariant quantity, not a Lorentz invariant, a frame-independent framework, we seem to be having some problems. One is this problem over here. So what will I observe in my reference frame and what will he observe in his reference frames? So somehow we cannot use exactly the same framework without a bit of a modification. We have to modify our frameworks. One modification is this one. Now, let me just jump a bit to something we will be discussing in a couple of hours. What is EMF created by? EMF is the work done on charges, right? But it's only the electric field that does work on the charges. So EMF created in a circular loop is nothing but E dot dl. Well, the flux is magnetic field multiplied by the area and d by dt. So this is what this law is about. So this simple system, just looking at this simple system, we have to conclude that if the magnetic field is changing, there should be an electric field somewhere. Again, let's go back to his reference frame. In my reference frame, it's easy to understand this. The magnetic field is constant, so we have magnetostatics. I already have tested magnetostatics. I know what's going on. So this rod, as it's moving, it will be pushing the electrons down. The magnetic field will be pushing the electrons down. So there will be a current running in the clockwise sense. Any questions on this one? So this is what in magnetostatics. Now let's come to magnetodynamics. Now his reference frame is now magnetodynamics because in his reference frame, the magnetic field lines are moving. They are not at rest. They are not static anymore. So what happens there? Still the electrons should be pushed down because in my reference frame, the electrons are moving down. He should be seeing the same thing. In his reference frame, the electrons should also be pushed down. Now the question is, what is pushing the electrons down? In his reference frame, the electrons are at rest. So it cannot be a magnetic force. So what is pushing the electrons down if it's not the magnetic force? If it's not the magnetic force, what is pushing it down? If V is 0, this term is not there. If there is a force, well, there is a force, something is pushing the electrons down, there is an electric field there. Now we identify a second source of electric field. There are no charges anywhere. There are no charges to create this electric field. In electrostatics, we only said that, okay, the electric field is created by charges, positive charges and negative charges. But now we see another source of the electric field, changing magnetic field. If the magnetic field lines are moving, or if the magnetic field is somehow changing, it creates an electric field. Okay, so this will be some of the consequences of our simple observations between these two reference frames. And then we will, of course, generalize it to other cases. So this law we had derived for this simple case, but now we will take one step further. We are looking for laws that are valid in every circumstances, not just for a special case. We will say that this is valid all the time, not for this one. This is the next step. Of course, if you make such a claim, you have to somehow prove it, demonstrate it experimentally. What will be the consequences of your claim that can be tested? Yes?
In his reference frame, the electrons on the other.
In whose reference frame? My or
In his.
his? Okay.
The other end moves to the opposite direction. So in his reference frame, there is actually
Which electrons are moving in which direction?
on the
Bottom, on the wire. Okay, so let's see. In my reference frame, the electron over here is moving like this, right? So in his reference frame,
in his reference frame,
the electrons will be moving.
still on the same direction, but in his reference frame, electrons on the other wire that contains the light bulb.
This one? Okay.
They actually feel the magnetic force.
No, it's in a region where the magnetic field is zero. The magnetic field is non-zero only in this region. Yep. This is the region where there is a non-zero magnetic field. Outside B is zero. So if you want, I can just... So in the light bulb, there is no magnetic field. Here B is zero. So they don't feel any magnetic force in his reference frame.
But I see the electrons going in zero.
So what will be the direction of the forces acting on them?
Down.
So they're not moving anywhere.
What?
They are not moving anywhere. The wire will just hold them
No, in the rod.
in the rod. Well, in your reference frame, let's say initially there is no current, then I moved. Initially there is no current, so there is no motion to start with. So in your reference frame, there is no reason why the current should be flowing. In my reference frame, there is a reason why the current should be flowing, but in your reference frame, there is no reason why the currents are flowing unless this law is valid. That's one. Okay, let's give a break and we will continue.